The talk is called Attacking File System Minifilters. A little bit of history about the talk before I actually get into the weeds of things. Why was I targeting Cloudfilter, as the name suggests? I was trying to compete in Pwn with my team, HD3 Labs, and I wanted to look at something that had a little bit of traction, like people have analyzed it. At the time, I wasn't very experienced with reverse engineering, so I wanted something with some information that I can kind of build up on and then move on from there. So a little bit about me. Currently, I'm a security researcher at Margin. Previously, I was at Atreides Partners, and before that, I was at Optiv. My hobbies, I like lifting weights. I like photography, not good at it. And security research with HD3 Labs. So, the agenda. In the start, I'll talk about the Minifilter landscape and Windows architecture, just so you guys kind of understand where we're dealing with things in the technology stack. Then we're going to talk about CloudSync, specifically the Cloudfilter driver and how it works. And then we're going to talk about the driver's attack surface, and then the bug hunting techniques used. And finally, we're going to review previous bugs and research recap. I should have updated the slide because after research recap, there's going to be like an additional few slides of the bugs that were discovered since I looked at this. So it should be fairly up to date. Now, let's discuss the Windows architecture. It looks something like this. Up above that dotted line, that's your user mode. Below the dotted line, that's your kernel mode in the OS. Typically, applications live in that application block. And when you do various syscalls or anything like that, they will go down the DLLs. It will go to NTDLL, which is where the syscall happens. And then there's a transition. It goes to the executive. And then finally, it will go IO manager, or at least with file system calls, IO manager, file filters, file system, and so on. So as the name suggests, we're going to be focusing on file filters. Now, what are Minifilters? They're these drivers that sit between your IO manager and your file system driver. They intercept file system operations. So your create file, your delete file, your rename, anything like that, they're intercepting it and inspecting what's happening. Now, what are they, or actually, sorry, going back up. Minifilters have a value or a attribute called an altitude. The altitude determines where this driver lives on the driver stack. Higher altitudes sit closer to the IO manager, whereas lower altitudes sit closer to the file system. Now, so some sample use cases. For security, you have like your EDR software and your encryption. And for creating backups, compression, and hierarchical storage management. Our focus is going to be hierarchical storage management, which is basically having data that can live on different like data sources or anything like that. So your file system and the cloud. Obviously, other like the security use cases, you want to intercept file operations. Let's say you're opening a handle to LSAS with all privileges. It will see that operation and reject it. Now, so basic file system terminology. You have your file system minifilter. That's the main driver. That's doing all your, interceptions and filtering. You have your filter message ports. They're used for asynchronous communication with the driver. You have your filter callbacks. These are the actual intercepted operations. So let's say you have a create file operation. With each callback, you have a pre and post. So in our example of create file, you can intercept before the creation operation, and then you can intercept after and do additional processing there. And finally, filter contexts. There's a handful of contexts that provide various information about various things. So you have your volume context, provides information about a volume. You have your instance context, provides information about the instance of the driver when it comes to that volume. You have your file context, stores information about a file. Your stream context stores information about the data stored in the file, about your file stream. And then you have your stream handle context. That's an open handle to a stream, and so on and so forth. I think there are 7 contexts in total, 7 different context types that are offered by the filter manager. And with cloud synchronization specific terminology, we have our sync route provider, our placeholders, and hydration. So, in layman's terms, what this technology, I guess, was initially designed for is your OneDrive application in Windows. So, you have your sync route, that's your OneDrive folder. You have your sync route provider, that's the OneDrive application. You have placeholder files. These are files that are in the cloud, but they're not on disk. And you have your hydration. Hydration is the process of filling those placeholder files out with their legitimate data. That's hydrating. Dehydration is the opposite of that process. Now, this is what your cloud synchronization architecture kind of looks like. You have your sync route provider on the top left. You have, in the green, you have just regular processes interacting with the files. And as you go down, you'll see, eventually we see Cloud Filter. The altitude is about 180,000. So out of the 13 loaded, I think at the time, 13 loaded, so as of March 2025, there were 13 filter drivers loaded by default. This is at number 8. So this is basically the middleware of your I/O operations. Now, the user mode components, you have your sync provider, once again, OneDrive application. It has a few dependencies. It mostly depends on your cloud API, .dll, and then that has a major dependency, which is the filter library, and then NTDLL. I can go on the different types that are defined, but there you go. So what do you need for sync route registration? You don't necessarily need a process that has medium integrity, but it was useful because for pwn to own, you need medium to system for the bug. And so this was a very good driver. All you need, I believe, is to set a reparse point on a folder. So that's, I guess, the barrier to entry. You need a folder that you can set a reparse point on that's going to act as a sync route. And I believe you need write permissions for everything under. So you can register a sync route with register sync route, and you can connect with connect. One thing that's interesting is we're going to talk about is callbacks. So there are filter callbacks, and then there's these callbacks that live in the sync route. The filter callbacks, before your create file operation, they get called. But let's say the driver got a file read operation on a placeholder file that wasn't hydrated, so it doesn't have data there. What the filter manager is then going to do is it's going to call one of these registered callbacks in the connect sync route function, and it's going to ask it for the data. So if in the case of a placeholder being opened, the filter manager is going to call your OneDrive application. It's going to say, hey, I need the data for this. The OneDrive application is then going to go talk to the internet, fetch the data, bring it back, and then provide it to the driver. So there's some interesting behavior. As you can see, it's asynchronous stuff kind of happening with the kernel, or like it's not very linear, and there's a few steps involved. So there's some interesting VR, I guess, surface there. Now, the cloud filter specific context, it uses an instance context, it uses a file context, it uses a stream context, and a stream handle context. Now, cloud filter attack surface. This is, I guess, what the most interesting part of the talk is. There's two main ways to talk to cloud filter. There is your intercepted operations, so your filter callback technique, and then there's your message port. Going over the filter callback surface, if you like the animation, it's the actual intercepted calls. I believe there are, yeah, about 15 operations registered. Some of them have pre and post callbacks. Some of them just have pre. I didn't bother listing those. You can, if you decide to research this, you can look at that. Interesting callbacks include your pre-read and write operations, you pre-create. So pre-create will, it's when you're opening a file or opening a handle to a file, that's when that gets called. Read and write, obviously, before you read and write. The most interesting one there, though, is your pre-file system control. So these are operations. It's kind of like your driver device I/O control, but it's happening on a file. And I believe it calls NTFS control file under the hood anyway. So most callbacks lead to that one function. And sorry. So yeah, looking at the pre-file system control callback, that's the, like we said, that's the most important one. There's 15 FS control codes, which are like ioctals when it comes to drivers. 11 of them buffered I/O, 4 of them neither I/O. If you don't know the different data transfer types between user mode and kernel mode in Windows, there's 3. There's buffered I/O, which copies the user buffer into a kernel buffer and then supplies the driver with that kernel buffer. There's direct I/O, which I believe maps the user buffer into the kernel. I'm not too sure about that. And neither I/O, which is the most interesting one. The raw user mode pointer is just going to be passed into the kernel, and the kernel operates on those. Obviously, the first place to look for bugs or interesting bugs is not neither I/O, because it's a raw pointer. I didn't find many bugs there, or I didn't find too complex of logic being done by the driver there. So your most important control code is your pre-HSM control, so pre-hierarchical storage management, what this driver does. That's your control code to control that. Under there, there's various operations that are done. There's your environment operations, your placeholder operations, property operations, and so on. Environment operations, you can create, convert, update, and query placeholders. So we already discussed what placeholders were. Here you can just create one, or when you convert, you get a regular placeholder or regular file, and you convert it into a placeholder query. Typically, you use it on directories, and it's like, hey, which placeholders do you have, etc. With sync root information, you have basic, provider, and standard. I can't tell you what these, like the exact data off of the top of my head, what these are returning, but they are listed. The least amount of information is in basic, and the most is in standard. Placeholders, you can query range states. So with placeholder files, you don't have to hydrate the entire file. You can decide to just hydrate offset hex 1000 to offset hex 2000. And the rest of the file can remain in a dehydrated state. So that's what your range state is. It's asking, hey, from this offset to this offset, is this hydrated? Your dehydrate and your hydrate, they're kind of self-explanatory. You can manipulate the sync state. So it's like, hey, is this folder in sync? Or is this environment in sync with the clouds? And then pin state manipulation, I believe that has to deal with, hey, this individual file, is it fully hydrated? Is it dehydrated? Things like that. That's what it's storing. I can't speak too much to the sync operations. Finally, property operations. This is a very interesting part to look for bugs. Why? Most of the cloud API is documented, except these 4. These 4, at least on the FS control part, they're not very documented. And by the time I actually started my research, well, there's 2 things. I didn't do my patch diffing. We're going to get into it later. There's like when we review previous bugs. But I didn't look at this before I did that research. I didn't patch diff before my actual research. So there's that. But by the time I looked at this, there were no bugs discovered on this part of the driver. So we'll get to it later. So this is not documented. It's harder to reach. And usually when things are harder to reach, people are going to be lazy and just not look there. I was one of those people, by the way. So, with correlation vectors, they're used to track telemetry information. So you can set and get the correlation vector that's stored. Now, the message port attack surface. There's like a few, I guess, families of stuff. With filter control, you can query the progress of an operation, or you can abort hydration. Keep in mind, this is your async stuff, mostly. Service commands, this part of the message port gets used to set up your sync route, delete it, connect and disconnect. So various state-related operations. Range info, we already talked about that, and the specific information about which offsets are hydrated versus not hydrated, they're stored in bitmaps, which are stored in the stream context. Acknowledging notifications, so let's say a rename or a delete or a dehydration of a file happened, the sync route provider needs to be able to be like, hey, I acknowledge that this happened. Transfer. So this is used for data transfer between the user mode and the kernel that is not through FS control file. Specifically, let's think of a scenario. You have your sync route provider set up. You have someone accesses the sync route. That's fully hydrated and it's all up to date. Great. There's a folder underneath that called placeholder folder 1 that's not hydrated. When that gets opened, the kernel is going to then call the sync route provider, specifically in the fetch placeholders callback. And it's the sync route provider will send data to the kernel, like which placeholders exist through the message port, through transfer. Specifically, should be in the second one, I think, transfer placeholders. There you go, operation 105. And your transfer data, that's basically being used like, okay, there's a dehydrated file on disk. Some guy opened it, and once you open it, you want the actual data to be transferred to that user. So the kernel calls user mode talks to cloud, fetches the actual text, and then that is provided back to the kernel, and then the kernel hydrates the file, and then the user is happy because they get their data. And now let's talk about some of the bug hunting strategies used. There are two main strategies. Both of them, I have a lot of critique towards myself on how I did them. So keep in mind, this is from an earlier time. There was fuzzing and reverse engineering. So with fuzzing, I built a very, very, very targeted dumb fuzzer for the HSM control code. And with reverse engineering, I basically, there were a few documented bugs by the time I looked at this, like I said. I would look for interesting bugs from there, and I would try to find variants. And finally, there's like code and process review. This is basically taking individual calls, going from the beginning of the function, the interesting function, let's say it's create placeholders, and go all the way to the end and just review an actual process. Now, this is what the fuzzer architecture kind of looks like. You have a watchdog process, an operation fuzzer, and an HSM control fuzzer. The architecture, I got this from an idea. There was Synactive in 2023. They fuzzed, or they competed in Pwn2Own, and one of their entries was actually in this driver. So I got the idea from there. I watched that talk. It turns out they had this setup. The operation fuzzer just goes create file, delete file, rename file, just various file operations. Your sync route fuzzer or HSM fuzzer, they didn't have something like that. They just built a regular sync route provider. And what they did was that watchdog, every minute, it will decide to kill and restart one of these two sub-processes. So it will kill or restart the sync route provider, or it kill and restart the operation fuzzer. For them, it led to use after free. For me, it led to nothing. So your HSM control packets, how that was reversed, it was, or how I built those for the fuzzer. It was a combination of reversing the kernel, but mostly reversing the user mode stuff because that was very documented. And I just basically followed our entry points down to your device IO control call, and I built various packets from that. And then I fed that to my Visual Studio. I put them in my Visual Studio project and manipulated them. How I found those various device IO control calls, found device IO control in IDA in the Cloud API, the user mode portion, and I just cross-referenced that, and I just started reversing from there. Now, mutations, if you've done a lot of fuzzing, you can see where things can be messed up here. Now, I mutated about 25% of the time. So I created a random number generator, and depending on how many arguments are being passed to the call, and 25% of the time, I would select a random one of those, and I would add values to it. Specifically, I was adding up to hex 100, and I was specifically mutating lengths and offsets. I thought those were interesting, just because at least the documented bugs at the time, and as we will see later, this driver was and is historically susceptible to a lot of heap overflows and out-of-bound bugs. Now, the message port behavior, this was not like looked at all. So this was, I just heard the guy from Synactive say his architecture, and I just implemented that. There was no real complex logic. I can't tell you what that message port looked like at the time I looked at it, or like what the packets looked like, and so on. So as far as this side is concerned, just think it's more fuzzing the environment. And the operation fuzzer, these are the different operations it was doing. Like I said, it wasn't even manipulating those. It was literally calling create file on those individual placeholder files. So nothing really crazy here. Now, with reverse engineering techniques, so here are some of the, one of them was cross-reference memmove. And I got about 111 cross-references to that function, which is your mem copy, by the way. It's the same argument, same everything. So I looked at that, and I created a list of all the operations and their offsets. And typically, I hunted for those when I would get burnt out, and like, I can't reverse that much here. Let me see if I can find a quick win. So I would go find a random mem move operation, and then I would go reverse around there to just, like, with these kind of things, you don't really need to pay attention to state as much, and you can see a heap overflow or like some kind of overflow through mem move. Also, like I said, there were a lot of bugs there, and the bugs, even up to this date, with these mem move operations, a lot of the time, your allocator and your move operation and all of the relevant information you need has been in the same function. So you can really quickly potentially look for bugs here. Additionally, there was like when I said variant hunting, there was that CVE with set pin state. Specifically, it was fetching a file path, and if a certain operating system feature is on, which is 64-bit file paths, typically in Unicode strings in the kernel, that value is being stored in a word rather than a keyword, which is a 64-bit. Well, there was an integer truncation bug where when it's querying the file path, the function, if 64-bit file paths were enabled, the function would return a 64-bit integer, but the logic of the driver actually still used, I believe, a word. So you have a very large truncation, and that led to, I believe, an overflow. Additionally, I hunted for use after freeze, and once again, general process review. The two that have stars on them, as far as general process review, I believe these are, since I looked at them, there were bugs discovered. So we're gonna quickly go over the bugs later. Now, with use after free hunting, there's different specific bugs I was looking for. I was looking for dangling pointers, missing locks, and incorrect lock types. And specifically, it says shared lock on free. Now, dangling pointers are self-explanatory. Something gets freed, you don't null out the pointer after. Missing locks. Okay, some resource that can be used by two threads. It's not being locked, so you have your race condition there. Shared locks, or incorrect lock placement, I've only seen this relevant to filters. So filters have two types of locks. You have your exclusive lock and your shared lock. When you want to do some kind of file operation, or sorry, some kind of modification, you're supposed to use an exclusive lock. So let's say you're trying to change the size of a file. You place the exclusive lock, change it. Or you're trying to delete something within that file stream. You place an exclusive lock and delete it. For shared locks, it's shared. The idea is two threads can enter and read the same data. So it's to make, if you have a read operation, it's so you won't lock out other read operations. So for shared lock, you use them for read operations, exclusives more for write and free and so on and so forth. So I was looking for shared locks on write operations. I can tell you this, when I looked at this driver, there was, like this was an idea I kind of came up with while I was looking at it near the tail end of my research. I can tell you that this bug actually did exist in the wild. It just existed on a different driver, a different filter driver. So this can be some kind of logic you hunt for. And we already explained the general process review. Now, let's explain the history of the bugs. The first person to ever look at this driver from a security perspective was James Forshaw back in 2020. He found a bug in create placeholders that allows you to create arbitrary placeholders, so arbitrary file creation. So there was a access check issue. So the driver wasn't checking DACL or permissions, and finally there was the arbitrary registry key creation. In 2021, 3 additional bugs were discovered. We have a pool overflow with specifically reparse point decompression. There was an interesting, the other one was interesting in the sense that the function was doing access checks on set reparse point, but there is another kernel, or like another syscall, or sorry, another device IO control or FS control code called set reparse point EX. The driver just was not intercepting it. So there you had some kind of ACL-ish bug. Only sync root providers should be able to modify reparse points of placeholders because they're managing these files. And finally for 2021, an out of bounds in get standard info just doesn't check size. 22, I couldn't patch diff all the bugs, so I'm sorry. For the first one, it looks like some kind of race condition relating to bitmaps. The other one, it's an integer overflow when processing sync root name. 2023, a lot more bugs. People started looking at this driver. So 6, we have use after free due to ERP cancellation. That's the one from Synactive that I briefly mentioned that I guess gave me the idea for the architecture. You have missing ACLs on placeholder creation. So on some stack overflow for the population context. Funny enough, like for that one, it was just a hard-coded stack value. The fix was literally put the population context in the heap. So that's an interesting patch. And an out-of-bounds read due to poor MDL arithmetic and correlation vector. So with correlation vectors, there's different types. I think there are 2 or 3. The first generation of correlation vectors was just, I believe, maybe 64 bits or so, smaller than the larger one. So it's basically led to an out-of-bounds read there. 2024, another 6 bugs. And then 2025, which is when I started researching, there was 1 bug discovered. Cool. The 1 bug was in 2025 was in the process commands, which is in the message port side of things. I didn't know what this was by the time I actually did my research at all, or even by the time I did my initial patch diff. This context was added last week. Now, interestingly enough, a handful of these bugs were discovered on the same thing, or not necessarily, but they're all relating to file identity and reparse point buffers. What is the file identity? File identity is actually specific, or seems specific to Cloudfilter. It's a hex 1000 buffer. You can store whatever you want in it. That data is stored in the reparse point. What is a reparse point? Reparse points, generally, it's a buffer or a tag you can add, I believe. I'm not sure if it's to files or streams, but it's one of those two. But for layman's terms, reparse points are generally used for symbolic links. So you typically set a reparse point to create a symbolic link or a junction in Windows. Minifilter drivers use reparse points to tag individual files. So when there's a file operation, it will go check the reparse point or so on and so forth to say, hey, this is a file I actually care about. Anyway, by the time I did my research, I'm running low on battery, so this computer might turn off any second. I just need a USB-C charger. Yeah. Okay, so there are these 4 CVEs. They're all related. I'll start speaking quicker. Oh, boy. All right, so some initial patch diffing. This initial bug, this is your, this is a blue screen.
Oh, I didn't do that. I just work here.
The initial bug was that integer underflow, which happened because a size of a reparse buffer was subtracted by 12. So if you have something under 12, it will loop. The reparse point is stored in a word value, so you can have a very clean heap overflow in the kernel because of this. Now, Microsoft fixed this by introducing this new function called reparse point decompress buffer. Here's what the actual patch looks like, So in the beginning, we can see that there's a check if this value is under 4. That value has an 8 being added to it, which is some kind of header value, and we can see in the actual decompression logic down there, the value plus 8 is where the allocation happens, and in the actual decompression logic, we can see it's minus 12, and that's where the bug actually is. Now, interestingly enough, if you saw the introduced functions from last time, they're here again. So Microsoft actually fixed the bug and introduced a new function that has another bug. And here's your pre and post. So the problem is a lot of these file identity and reparse point buffers, they're very static. The file identity is hex 1000 all the time if it's like max. The reparse point buffer, hex 4000 max. So they're doing a lot of these allocations with just this hex 4000, and then if the user mode size is not, or user mode controllable size value is not being checked, that's it. That's your heap overflow, and so on and so forth. So similar behavior. Just see, this one is with file identity, a new comparison against hex 1000. There it is. So it's an allocation of size hex 1000, and then the user controls that size. There you go. That's your mem move. That's your heap overflow. Finally, there's this another integer overflow. A lot of places were not checked. After doing a little bit more reversing, we can narrow down to the interesting functions: acknowledge notifications, create placeholders, convert placeholders, update, etc. Now, here's your pre and post patch sample. You can see just a lot more logic added, but finally, when we add symbols, we can see it's the file identity. It's checking if it's greater than hex 1000, which will create your overflow in the check that's right here. Now, finally, research recap. I spent about 1.5 months on this target. All of the patch diffs you saw and you will see in the future have been done after my research window. So I have now a lot of context on where to look and what to look for that I didn't before. But by the time I had it, I had 0 bugs. I got a lot of experience and I had a lot of fun and heartbreaks. I found various memmove, like weird logic around memmove operations, but they're just not exploitable. So you might run into those. So in the research recap, what would I do differently if I looked at this driver? Reverse engineering based approach that I would change. When I'm hunting for use after freeze, before I didn't understand Minifilters very well, so I was looking for like an issue in processing the the filter manager managed structures, like your context. The problem is, technically these are out of scope. These objects are managed by the filter manager, not the driver I'm looking at. And a lot of the time I was looking through the destructor of these objects and I'm like, oh look, there's a dangling pointer here, without realizing like, okay, this doesn't even exist anymore. I can't reach it even if there is a dangling pointer. So a lot of time was wasted looking at this. So instead, what I would do when I'm hunting for use after freeze, look for objects that are not managed by the filter manager, and these are objects that are purely within the context of this driver. This could be your population context, your compressions, your bitmaps, and soon we'll realize is your sync root state. Are you connected versus disconnected? And look for variants of not so exploit areas. I looked for a variant of one bug really. Look for others. Go do some more patch diffing on other bugs and then find interesting stuff and follow that. Additionally, something that's tedious, actually look through all the memmove operations. Something that you'll find quite nice is there was a heap overflow since. So we can, this is a legitimate approach. There were other heap overflows in the past, but they still exist. And this heap overflow that we're gonna soon discover is like, it is from the November, December patch. So it's quite recent. And other additional things that I would change for success, well, one, for your HSM control, actually nail down the packets a little bit better, but let's say they're pretty good. I would tune my fuzzer to discover previously discovered bugs. I would have found potentially some out of bounds if my fuzzer was a little bit better. If I, instead of just adding hex 100, I can potentially use, like, given a -1. I didn't even add some logic that was basic like that. So when I actually put my fuzzer against an older version, I actually could only find the use after free at the time. So had I given a -1 for the size of the file identity at some point, I could have potentially found that, well, it was too late, but I would have found that, or at least rediscovered that file identity bug with the size, it was an integer overflow. I couldn't find integer overflows. That's what I was trying to say. And additionally, add support for the callbacks, because that's an entire, like, that's the other half of the driver that I just did not look at as much. Add support for reparse points. As we saw earlier, 4 bugs were in that same, like, reparse point logic. And it was literally initial functions, they introduce patches, bugs in the patches, and then once that area is clean, a little later down the road in that same processing logic, there's another heap overflow or something like that. So perform additional fuzzer tuning. And now, here are all the bugs that were discovered since I actually looked at the driver. There was, if I can do the math, actually that very last, those 2 there, so there were 7 bugs. We have a time of check, time of use in the processing of placeholder names. We have information disclosure through eProcess leak. There was another instance of that information disclosure. I just wanted to pick the simplest one for an example here. That heap overflow, that was discovered in December. That was in the properties operations When I said earlier, like, hey, look at this area that's not so documented. People have looked there less. Well, as I guessed, people looked there, and there was a bug. There might be others. There's 4 major property operation functions. 0 of them are documented, and now there's, this is the first bug that was discovered in that area. There's additional mem-move operations in that area, by the way. And yeah, we can see that only 1 bug was discovered. Potentially go look there for interesting stuff. They use after free with this sync-root disconnection and some out-of-bounds bugs because of placeholder, update placeholders. Oh man, I do not think this was charging. Anyway, so I ran out of charge, but that's fine. I can explain. Unfortunately, you can't see the demo now. So there was a demo. I can explain the time of check, time of use. So the time of check, time of use that on placeholder creation, James Forshaw found that initial bug back in 2020. What Microsoft did to patch that was how James Forshaw got to arbitrary file creation was he can set a reparse point in a folder, and your create file, when you're creating a placeholder, follows reparse points. So he basically provided a reparse point under the placeholder, under the sync root, and then created a file. So Microsoft was like, okay, let's be slick and let's patch this by checking if there is a file separator in the file name. Later, there was a function that it would be cool if I can actually present this, but there was a function called probe, memory manager probe and lock pages. I looked at that function. This is one of those bugs I missed. I looked at the name of that function and I said, hey, this is being called on a user mode buffer that's being passed to the kernel. It's lock pages. So it probably means this data is no longer, this data is immutable. Turns out that's not what that function does. The probe and lock pages, what it actually does is it just makes sure that memory does not get paged out, rather than, so it's locking that actual physical memory. So there was a time of check, time of use, where you just quickly add and remove the file path separator, and then you can re-exploit the bug from 5 years ago. Nobody discovered it in 5 years and up until like September of last month. So, last year. So good stuff there. What else did I want to talk about? I think we're getting close, actually. Anyone have any questions? Yep. Cool. Thank you. Okay. Oh, okay, yeah, sure.
You mentioned some new bugs being introduced via patches. Are there new features being added to this very often? Like, what's the rate of development? Is it changing a lot, or is it mostly just maintenance?
There was a high rate of development between 2020 and 2023. It seemed to have slowed down. Oh, okay, so the question was, what is the rate of development on this driver or surface? In the start, there was a lot. So like patch diffing those older bugs, some of them were annoying because like 13 functions would change and there's just one bug. So yeah, those were actually one of the bugs that had just a bunch of question marks. That it's 13 functions change. Right now, not very much. What you're seeing a lot these days is usually just bug patches. However, something Microsoft did get a lot better at, a lot of these bugs, when they are being patched, they're patching so that use after free, you saw, there were like 3 or 4 different code paths that were vulnerable. They patch the entire thing. Yes? Thank you.
So I was curious, do you think trying to implement your own mini filter driver first to learn kind of the techniques and format, would that have been beneficial, you think, or would it have actually slowed you down?
I mean, I don't think, this isn't like if I was looking at something more complex, like a PDF parser, or like a JavaScript engine, or some kind of interpreter or something like that, sure. or even more operating system like design bugs, yeah, sure, I would have re-implemented this driver. Of course, re-implementing it would make you better at it, and you'll find bugs and hunt for bugs more efficiently. But I don't think it's needed here. I think
The whole driver, just learning the general mechanics of how a mini-filter driver performs simple, like reparse points, for instance, right?
Okay. Yeah, it would have helped. You can go two approaches. You can go that approach, and I can tell you right now, like I got a lot better at this just by patch diffing. If you're not a great developer or you're just not interested, you're more excited by bugs, just go patch diff and trigger the other bugs, and you should be fine there. Oh, there's one here.
So you mentioned that your fuzzer, you could have been better with your fuzzer.
Yeah.
So you didn't pass in a -1.
Yeah.
You clearly did a lot of analysis on patch diffs. Do you think, in terms of process of getting better at this, do you think that it is a fruitful strategy to look at the patch diffs and go, okay, my fuzzer doesn't do the thing that would have triggered that particular bug that they patched? Look at each one and then improve your fuzzer based on what you're seeing in all the patch diffs. Is that something you considered, or is that a lot of work? Is it too much work, or is it, I'm just kind of curious
So
about
yeah, two things. I view the surface, especially now that I'm speaking about it, I view the surface as purely like information shared. So I won't be hunting unless I'm gonna make the bug public later. I won't necessarily be hunting on the surface. That's one. Two, that's actually the term is fuzzer tuning. And yes, it would have been very, very, very helpful if I tuned my fuzzer to discover these bugs. Additionally, the fuzzer, I wasn't really doing this complex fuzzer campaign. I actually built the fuzzer for 2, maybe 3 reasons. Reason 1, let me understand the different components or different functionalities of this driver. Reason 2, I wanted structures, so when I go patch or reverse the driver, I can just do it more intelligently and figure out what's going on a little bit better. And really, the fuzzer, there was no additional, again, there is no fuzzer campaign. So when I was doing my fuzzing, it was, I reverse during the day, and when I go to sleep, I turn on this really bad program that I built, and I go to sleep, and then I wake up, and then I continue reversing. That's what the fuzzer really was. So.
The patches that you analyzed, in your experience, did they seem to be very targeted patches to fix the bug, or were there other changes rolled in that made it difficult to figure out where the vulnerability was that was fixed in the patch?
Oh, to figure out where the vulnerability was.
I mean, sometimes patches are huge.
Okay, yeah.
Which function actually fixed the vulnerability? Or was it super simple?
Very good question. So this is a more interesting thing that I learned after patch diffing for so long. So the question was it kind of simple, if I understand you correctly, was it simple to find the bugs when doing the patch diffing? Yeah. Before 2022, Microsoft used to just patch the bugs and not say any information about them. It would just be like, CVE this is the CVSS score. What's nice is after that year, Microsoft started introducing another value to their CVE board thing, and they give you the CWE. They tell you it is an integer overflow, it is an out of bounds, it is a use after free. So you can go hunt for things a little bit better. Additionally, I know I can't pull it up right now, but from the previous images that I did have, Microsoft right now, with a lot of these patches and new code introductions, you will see a feature underscore and 8 numbers. Go cross-reference those functions. Those usually are the patch. So Microsoft, when they're introducing the patches, they're not just adding the code. They're adding an if-else statement. If this patch exists or is on, run this new code. Else, run the old code. I think that's just for they make sure the patch to run the patch against 2 million systems and make sure like not the patch doesn't introduce any new bugs, the patch itself. So yeah, that's what's going on there. They're quite, especially after 2023, they're very easy to find. It's quite nice actually.
Awesome. Thank